When we gaze up at the night sky, we are met with a breathtaking tapestry of stars, planets, and distant galaxies. Each point of light tells a story, a tale of cosmic events that have unfolded over billions of years. The night sky is a window into the vastness of the universe, a reminder of our place in the grand scheme of things, but what we see is only a fraction of what is truly out there. Beyond the visible spectrum lies a hidden universe, filled with wonders that our eyes alone cannot perceive. This unseen universe is teeming with phenomena that challenge our understanding and push the boundaries of our knowledge. Hidden among the stars is a vast and mysterious realm, the interstellar medium. This enigmatic expanse is not just empty space, it is a dynamic environment where the building blocks of stars and planets are forged. The interstellar medium is a cosmic laboratory, where the raw materials of the universe are mixed and transformed. This region between the stars is far from empty. It is filled with a complex mixture of gas and dust, creating a rich tapestry of interstellar matter. These components interact in ways that are both subtle and profound, influencing the formation and evolution of celestial bodies. It is teeming with a diffuse mixture of gas and dust, collectively known as interstellar matter. This matter is the lifeblood of the galaxy, fueling the birth of new stars, and the creation of planetary systems. Without it, the universe as we know it would be a very different place. While the gas, mostly hydrogen and helium, makes up the bulk of this interstellar material, it is the seemingly insignificant dust that holds the key to understanding the universe's grandest structures and the very processes that gave birth to our solar system and life itself. These tiny particles, often overlooked, are the seeds from which stars and planets grow. Interstellar dust, though minuscule in size, plays an outsized role in shaping the cosmos. It acts as a catalyst for the formation of complex molecules, which are the building blocks of life. Dust grains provide surfaces for chemical reactions to occur, leading to the creation of organic compounds that are essential for life as we know it. It is these tiny particles, often no larger than a grain of smoke, that serve as the building blocks for stars and planets, the catalysts for complex molecules, and the very fabric upon which galaxies are woven. The role of interstellar dust extends beyond mere construction. It influences the thermal balance of the interstellar medium and affects the propagation of light through space. In this exploration of the cosmos, we will delve into the fascinating world of interstellar dust, uncovering its origins, its profound influence on the universe as we know it, and the secrets it holds about our own cosmic heritage. Join us as we journey through the unseen universe, revealing the hidden wonders that lie beyond the reach of our eyes, and discover how these tiny particles have shaped the cosmos in ways we are only beginning to understand. The origins of interstellar dust can be traced back to the fiery crucibles of stars themselves. These cosmic forges scattered across the universe are the birthplaces of the very dust that eventually coalesces to form planets, moons, and even the building blocks of life. Stars, those colossal nuclear furnaces, spend their lives fusing hydrogen into helium in their cores, releasing unimaginable amounts of energy in the process. This energy not only lights up the universe, but also drives the complex processes that lead to the creation of heavier elements. As stars age and approach the end of their lives, they begin to shed their outer layers into the interstellar medium through stellar winds, or, in the case of massive stars, through spectacular supernova explosions. These dramatic events are not just the end of a star's life, but the beginning of a new cycle of matter in the cosmos. These expelled stellar envelopes are enriched with heavier elements forged in the hearts of stars through nuclear fusion. The process of fusion in stars creates elements like carbon, silicon, oxygen, and iron, which are essential for the formation of planets and life as we know it. Elements like carbon, silicon, oxygen, and iron are scattered into the interstellar medium, where they cool and condense into tiny dust grains. These grains are the seeds from which new stars and planetary systems will eventually grow. These grains, composed of refractory materials, are incredibly resilient, capable of withstanding the harsh conditions of interstellar space. They travel vast distances, carried by interstellar winds, and can survive the intense radiation and shock waves that permeate the cosmos. Supernovae in particular are prodigious dust factories, seeding the interstellar medium with vast quantities of heavy elements. The explosive force of a supernova can propel these elements far and wide, enriching the surrounding space with the raw materials needed for new stars and planets. These elements are the building blocks not only for future generations of stars and planets but also for the complex molecules that are essential for life. The dust and gas clouds that form from these elements can collapse under their own gravity to form new star systems, continuing the cycle of stellar birth and death. Thus, in a sense, we are all made of stardust, forged in the hearts of long-dead stars. The atoms in our bodies were once part of ancient stars that lived and died long before the Earth was formed. This cosmic connection reminds us of our place in the universe and the incredible journey of matter through time and space. Interstellar dust plays a pivotal role in the formation and evolution of galaxies. In the early universe, vast clouds of primarily hydrogen and helium gas coalesced under the influence of gravity. As these clouds contracted, they began to rotate, forming swirling disks of gas. Within these disks, interstellar dust played a crucial role in cooling the gas and allowing it to clump together. Dust grains are incredibly efficient at absorbing and re-radiating energy. When ultraviolet radiation from nearby stars or the intense radiation field surrounding active galactic nuclei interacts with dust grains, the grains heat up and re-emit this energy in the infrared portion of the electromagnetic spectrum. This process of radiative cooling is essential for star formation as it allows the collapsing gas clouds to shed energy and contract further, eventually reaching the temperatures and densities required to ignite nuclear fusion. Without interstellar dust, the early universe would have been a much more chaotic and less hospitable place. The cooling provided by dust allowed for the formation of stable, rotating galaxies like our own Milky Way, paving the way for the emergence of stars, planets, and ultimately life itself. Stellar nurseries, the role of dust in star birth. Interstellar dust is not merely a passive bystander in the process of star formation. It is an active participant, shaping the environments in which stars are born and influencing their properties. As mentioned earlier, dust grains are incredibly efficient at absorbing and scattering light, particularly at shorter wavelengths such as ultraviolet and blue light. This scattering of light by dust is what gives rise to the beautiful and varied colors we observe in nebulae, the cosmic clouds of gas and dust where stars are born. Within these stellar nurseries, dust plays a crucial role in shielding nascent stars from the harsh radiation of their more massive siblings. This shielding allows protostars, the embryonic stage of star formation, to accrete material from their surroundings and grow in mass. Moreover, the presence of dust grains within these collapsing clouds facilitates the formation of molecules, including complex organic molecules that are the building blocks of life. Planetary cradles dust, and the formation of planets. The universe is a vast and dynamic place filled with countless wonders and mysteries. Among these, the process of planet formation stands out as one of the most fascinating and complex phenomena. It all begins with dust, the seemingly insignificant particles that play a crucial role in the birth of planets. The story of interstellar dust does not end with the birth of stars. It continues into the formation of planetary systems. When a star is born, it is often surrounded by a dense cloud of gas and dust. This material, left over from the star's formation, is the building block for planets. Over time, the dust particles within this cloud begin to collide and stick together, forming larger and larger clumps. As a young star ignites nuclear fusion in its core, it creates a powerful stellar wind that blows away the remaining gas and dust in its vicinity. This stellar wind is a force to be reckoned with, capable of clearing out vast regions of space. However, not all of the material is swept away. Some of it remains, clinging to the gravitational pull of the newborn star. However, a small fraction of this material survives in the form of a circumstellar disk, a swirling disk of gas and dust that orbits the newborn star. This disk is a dynamic and ever-changing environment where dust particles continue to collide and merge. Over time, these collisions lead to the formation of larger and more complex structures. Within this protoplanetary disk, as it is called, dust grains begin to collide and stick together, a process known as accretion. Accretion is a slow and gradual process, but it is incredibly important for the formation of planets. As dust particles stick together, they form larger and larger clumps, eventually becoming pebbles, rocks, and even boulders. These tiny aggregates of dust gradually grow larger, forming pebbles, then boulders, and eventually planetesimals, the building blocks of planets. Planetesimals are small, solid objects that can range in size from a few kilometers to hundreds of kilometers in diameter. They are the precursors to planets, and their formation is a critical step in the planet-building process. Gravity then takes over, pulling these planetesimals together to form planets and their moons. The force of gravity causes these objects to collide and merge, creating larger and larger bodies. Over time, these bodies can grow to become full-fledged planets, complete with their own moons and other satellites. The composition of a planet, whether it is a rocky terrestrial planet like Earth, or a gas giant like Jupiter, is largely determined by its location within the protoplanetary disk and the types of materials available for accretion. Rocky planets tend to form closer to the star, where temperatures are higher, while gas giants form further out, where it is cooler. The presence of dust in these disks is essential for providing the raw materials for planet formation and for shaping the architecture of planetary systems. Without dust, planets as we know them would not exist. Dust is the foundation upon which planets are built, and its role in the formation of planetary systems cannot be overstated. From the smallest grains to the largest planets, dust is the key to understanding the origins of our solar system and beyond.